Assalamu alaikum dear researchers and welcome to another episode on PLS SEM with Smart PLS 4. Today we are going to discuss about unobserved heterogeneity and how to uncover it using finite mixture or FIMIX model for PLS SEM. Heterogeneity or differences that arises in data can be either observed or unobserved. When differences between two or more groups of data relates to some observable characteristic such as gender, age or country of origin, this is called observed heterogeneity. Researchers can use these observable characteristics to partition the data into separate group observation and carry out group-specific PLS SEM analysis such as MICOM for measurement model and PLS MGA and permutation to find out if there are differences in group as in regard to some path coefficient. This is we have already discussed in our previous lecture related to moderation. On the contrary, the unobserved heterogeneity implies the differences between two or more groups of data do not emerge from a priori from a specific observable characteristics or combination of several characteristics, but they become apparent when differences in structural path coefficients are observed. If you find that you have enough segments in your model, you may need to run a multi-group analysis where you need to check if there is a difference between the results in both segments, and before that you also need to run the MICOM to check if there is a measurement model invariance that is present due to the both segments. Because if we do not tackle the hidden heterogeneity in our model or measurement model, it may affect the parameters and estimate of our structural model and thereby invalidates our result. So that is why we need to understand what is the unobserved heterogeneity in our data. Traditionally, the heterogeneous data structures is basically found from the using cluster analysis method, for example k-mean clustering. However, these methods does not account for measurement and structural model relationship, and this is a major drawback of these approaches. Moreover, traditional clustering approaches perform very poorly regarding identifying group differences. So acknowledging these limitations, there are certain methodologies in PLS SEM and they are being proposed such as the latent class techniques or response-based segmentation techniques. These techniques have proven very useful to identify unobserved heterogeneity and partition the data accordingly. The first and most prominent latent class technique is finite mixture partial least square or FIMIX-PLS SEM. As indicated by its name, the approach relies on the finite mixture model concept, which assumes that the overall population is a mixture of group-specific density functions. The aim of FIMIX-PLS is to disentangle the overall mixture distribution and estimate parameters of each group in a regression framework. Now, this exhibit shows that this is a mixture distribution that FIMIX-PLS SEM aim to separate into segment-specific distributions. Before we proceed to analysis in PLS SEM software, let's take a look at the setting of FIMIX-PLS procedure. First of all, we need to use a stop criteria of 1 into 10 to the minus 5 and a maximum number of 5000 iterations, which are a sufficient number to get the iterations done. Then use the best solution of 10 repetitions to avoid convergence on a local optimum. When the indicators have missing values, we should use case-wise deletion. We are not supposed to use any mean value replacement or any other computation method in this case. To define a range of reasonable segment numbers, we use one segment as the lower bound and the larger integer when dividing the sample size by the minimum segment size sample as the upper bound. So sample size is important in this case. So for analysis, we are going to use this corporate reputation project that is already installed with PLS SEM software, or you can install it using the sample project, advanced PLS SEM book and corporate reputation model here. And what we are going to do is that we are going to go to this calculate option and finite mixture segmentation. Here the stop criteria is going to be 10 raised to the minus 5, maximum iteration 5000, and we are going to start with the one segment solution and number of repetition will be 10 and start calculation. On the left hand side, where we are going to select first of all model selection criteria, and this we are going to copy to Excel. So let's see how these model selection criteria are going to help us to determine the number of segments. So there are multiple model selection criteria. First of all, we need to look at which of these are important and how to consider which of the segment solution is the best or most optimal. Entropy or EN should be greater than 0.5. So preferably, first of all, we are going to look at entropy values. It should be greater than 0.5. So we retain that and follow the other model selection criteria. Except for entropy, the lowest value of fit indices is the optimal solution. So for any model selection criteria, the lowest value is a better value. If AIC3 and CAIC indicate the same number of segments, choose that solution. So it's a very simple and straightforward. If there is a chance that AIC3 and CAIC have the same number of segments or the same values, then we choose this solution. Alternately, jointly consider AIC3 and BIC. Also consider the segment number as indicated by AIC4 and BIC. Generally choose fewer segments than indicated by AIC, or choose more segments than indicated by MDL5. And last but not the least, we are going to see with our exercise as well that segment size should meet the minimum sample size requirement, so that if all other criteria are fulfilling but the segment size does not meet the minimum sample size requirement, then we are going to discard that solution. So here I have copied one segment solution to Excel, and then I'm going to rerun the model and finite mixture segmentation. Number of segments are increased to 2 and start calculation. Now here we also need to see the segment sizes. Here segment size is 0.515, 0.485. So if you consider that our initial data is 336 and we have used case wise deletion data, so related to 336, if we say that the segment size is 0.485, we are going to run the calculator. So you can use any criteria like the path coefficient or minimum R squared criteria or 10 times rule. So 336 into 0.485 is like 163 number of people, or in the segment size is 163. So this seems like an optimal number that we can still consider. And you can also make a separate table for the segment sizes for each time you run the FIMIX procedure. So I'm going to repeat this process and fill up my table for at least 5 segments. So here I have filled up the model selection criteria in the Excel sheet with 1, 2, 3, 4 and 5 segment solutions. Every time I've run the FIMIX model and then copy pasted all these values over here. And now these red highlighted are the ones that are the minimum values for each solution. So as you can see, first of all, I've highlighted those model selection criteria which are more important. En should be greater than 0.5. So, and the largest number is for 5 segment solution. Then unfortunately, as indicated, AIC3 and BIC does not indicate the same number of solutions. So the values are different in each case. So we cannot consider that option. Similarly, AIC3 and CAIC also does not indicate the same solution. So we cannot consider that option as well. Alternatively, according to AIC, the 5 segment solution is suggesting that now this is the lowest. So definitely we think that the correct number is likely to be lower than this 5, as we have already discussed. So if AIC is suggesting 5, then the correct number solution should be lower than 5. Similarly, both CAIC and MDL5 are suggesting a 1 segment solution, which, as we have already discussed, suggests that 2 or more segment or greater number of segments should be considered. So we can also go to further analysis with this criteria of AIC4 and BIC. Over here it suggests a 2 segment solution, which should be considered seriously. But if we look at the entropy for 2 segment solution, the entropy is less than 0.5. So here we have like quite confusing result, not indicating a best solution. So another way that we can find out some consistency is to see the minimum value in the sum of AIC3 and CAIC. And then what we can do is we can create this another row and add a sum of both these indices, and then we can see that once again this is indicating to the 2 segment solution. Now, although this is one way that some of our results are indicating a best solution, some of our results are not. Another way that we also need to keep in criteria is to look at the sizes of the segment, because we don't want a segment size that is too low or that is below the minimum threshold of the required sample size. Whatever the criteria you are using to select the sample size, either it is R squared value or either it is the path coefficient values that we have discussed in previous videos, or you are using the 10 times rule, you should also look at the sample size for each solution. So as you can see, for For two segment solution, now this table indicates the percentages that you can find in your PLS results. Here in the solution you can see the segment sizes over here. Now this is 5 segment solution, so segment size is over here, and I have copied it in the Excel file, and this is actual value because it is multiplied by 336, the total sample size. So for two segment solution, this one needs to be like this. For two segment solution, we have this is for segment 1, this is for segment 2. For 3 segment solution, now as you can see the size of segment 3 is very small. Again for 4 segment solution, the size of segment 3 and 4 both are very small, and for 5 segment solution, 3, 4 and 5 are yet again below the threshold of the sample size. So as this segment is too small, what we can do is either we can drop these segments, or we can consider that solution which has a larger segment size in return. So that is segment 2 seems to be the best solution over here, although the segment 2 is not indicating as per the entropy values. Other indicators are actually reflecting towards segment 2. One of the interpretation that we can do is that we can interpret that the overall there is no heterogeneity in the data, because our fit indices are returning confusing values, and we can proceed with a 1 segment solution as well, or we can also take up a 2 segment solution over here if we want to find out that how the data is or which of the already present heterogeneous observed heterogeneous criterias correlates or matches with the heterogeneity of 2 segment solution as we have found in our data. Before making our decision, we are also interested to know that how the R-square values and the path coefficient differ for this 2 segment solution, because we have already discarded the other segments. So we are deciding between the 2 segment and 1 segment. So if we open the report, this is for a 1 segment solution. So the R-square value are over here. Dependent variables is over here. So we can copy this to Excel. This is R-square value for 1 segment. Now I'm going to copy the results for the 2 segment. Now these are R-square values for 2 segment FIMIX. This is for segment 1, this is for segment 2, and then weighted average R-square. So here you can see the results for the segment specific R-square values along with the weighted R-square, and R-square values for each segment separately. And you can see that the weighted average R-square for 1 segment solution and 2 segment solutions are not that different, although there is a bit of it is higher in 2 segment solution. But if we look at this, there is a considerable difference in segment 1. The R-square values are quite high as compared to segment 2. So in this case, our case is tilted towards the 2 segment solution, but yet since the weighted average R-square values are not that different, again it is creating a bit of confusion. We can look at the path coefficient values as well. So we can see that for both segments there is a difference in the path square in the path coefficients. Specifically, if you look at how CUSA affects CUSL, over here is 0.585, 0.421. So there's a difference. Similarly for ATTR in CUMP segment 2, this is the value. For segment 1, this is the value. So there is a difference in path coefficients, and there's a considerable difference. So we can overall in combination we say that our results suggest a bit of heterogeneity. Although the heterogeneity is not that prevalent, we can go both ways. We can also select a homogeneous sample, and we can also select a heterogeneous sample. However, if you are wondering that what does this FIMIX tells us about, the FIMIX has indicated that we can refer to the 2 segment solution. We can also refer to a 1 segment solution, but there is another prediction method that is called POS, or prediction oriented segmentation, which we are going to run this procedure to check if the 2 segment solution is the optimum solution. So FIMIX is always run in combination with the PLS POS, or prediction oriented segmentation process. One of the reason is because FIMIX-PLS has its own limitation. It can only capture heterogeneity in the structural model relationship, and cannot account for heterogeneity when it comes to measurement model, which is why it is uselessness can be overcome when we use it in combination with the prediction oriented segmentation, or PLS SEM, to explain the latent segment structure and estimate the segment specific model outputs. So in the next lecture, we are going to discuss the PLS-POS procedure. Anyways, we are interested to find out that if it's a two-segment solution, which of this with what existing data it correlates. So what we are going to do is, as you can see with the segment sizes, almost 51% is in segment 1 and 48.5% in segment 2. And this is segment assignment report, and you can see that this shows the probability of being in a part of or membership of any segment. We are interested to see a discrete segment assignment, that what if you are forced to be a part of a group, which segment you are going to be a part of any group. 2 means segment 2, 1 means segment 1, and this is for the whole data. So I'm going to create a new data file over here. I'm going to give it a new name, new FIMIX 2 segment, and uncheck probabilistic assignment, uncheck others, and manifest variable scores and segment assignment is that I need here, and create a new file. Now new data file is created. You can open it via Project Explorer. Now double click on this and click on indicator correlations, because I'm curious that what is the reason that these two segments are present in the data. Now copy this to Excel, and so what we are interested to find out is that which of these variables have a high, low, or positive or negative correlation with discrete segment assignments. So as you can see that this 0.253 is a bit substantial, although a quick look at the data does not show any high correlation way above 0.5 or way above 0.7, which again reiterates our point that segmentation may not be present in the data as such, but maybe it's a combination of multiple indicators. But here we can look that for ATTR3 question, this is 0.253. So similarly 0.275 here for CSOR4. So we were interested to find out if there is anything that is way above 0.55, so we can say that that is a high and low values of those particular segments, and we can generate data or group indicator based upon those results. Like what we can do is that we can in this we can generate groups based upon the discrete segment assignment, apply, and we can also name that high and low or group 1 or group 2 based upon that particular characteristics. So this is all about FIMIX. We'll carry forward with POS in the next video to understand the whole process of unobserved heterogeneity.